the most relaxing facts about the universe. Chapter 1. Drifting into the Universe. Welcome. Settle in for a moment. Let your shoulders soften, let the day slowly dissolve, and allow your thoughts to become lighter. Tonight, we're not rushing anywhere. We're not solving problems or chasing headlines. We're simply drifting outward, past the room you're in, past the city lights, beyond the blue curve of Earth, into something far older and far quieter than anything we've ever known. We're going to explore the universe. Not just a star or a single galaxy, but the vast, expanding totality of it all. Along the way, we'll move gently, almost like floating, touching on black holes, ancient light, wandering planets, and mysteries that scientists are still carefully unfolding. Some ideas may feel solid and well-measured, others may remain beautifully unresolved, like distant lights at the edge of vision. If these journeys help you rest or spark your curiosity, you can always return here again. For now, just breathe and let's begin. Most astronomers estimate that the universe is about 13.8 billion years old. That number comes from careful measurements of the cosmic microwave background, the faint afterglow of the early universe, and from observing how quickly space itself is expanding. When we measure distant galaxies, we see them moving away from us. The farther they are, the faster they recede. It's as if the fabric of space is stretching, carrying galaxies along like leaves on a widening river. But science is rarely a finished story. In recent years, subtle tensions have appeared in our measurements. Different methods of calculating the universe's expansion rate don't perfectly agree. Some observations of early galaxies suggest they may have formed faster or earlier than expected. Does that mean the universe is older than 13.8 billion years? Probably not. But it does mean we may be missing something. Perhaps dark energy, the mysterious force driving expansion, behaves in ways we don't yet understand. Or perhaps our cosmic models need gentle refinement. It's a reminder that even our best answers sit within a larger horizon of uncertainty. Now imagine drifting through the Milky Way, far from any sun. Not every planet belongs to a star. Some worlds roam alone. These are rogue planets, worlds that either formed in a young solar system and were later flung outward by gravitational chaos, or perhaps condensed directly from collapsing gas clouds without ever igniting into stars. They wander the galaxy in darkness, untethered and cold. Without a nearby sun, there are no sunrises or sunsets. No warm glow, only faint starlight scattered across an endless sky. Astronomers suspect there may be billions of these solitary worlds in our galaxy alone, possibly even outnumbering the stars themselves. We detect them only when they pass in front of background stars, briefly bending and magnifying the light through gravity. Otherwise, they remain nearly invisible. Each rogue planet is a silent traveler, spinning through interstellar night. It's a strange thought, entire worlds adrift between the stars, unseen and unknown. And what about the universe itself? Does it move in cycles? The standard cosmological model suggests that the universe began in a hot, dense state we call the Big Bang, and that it will likely continue expanding indefinitely. Over unimaginable time, galaxies may drift so far apart that the cosmos grows dark and cold. But some theoretical models imagine something different. In certain bounce or cyclic scenarios, the universe doesn't expand forever. Instead, after reaching a vast maximum, it might eventually reverse, collapsing inward, compressing into an incredibly dense state, and then expanding again. A cosmic heartbeat, expansion, contraction, renewal. These ideas are speculative, and we don't yet have evidence that such cycles occur. But they offer a poetic possibility that what we call the beginning may not have been the first beginning, that our universe could be one chapter in an infinite sequence, each era leaving subtle imprints on the next. It's a humbling thought, not a single story, but a rhythm spanning eternity. If we look far enough into space, we also look back in time. The oldest light we can observe comes from about 380,000 years after the Big Bang. Before that, the universe was a searing plasma, a fog of charged particles so dense that light could not travel freely. Photons scattered constantly, unable to move in straight lines. Then, as the universe expanded and cooled, Electrons combined with protons to form neutral hydrogen atoms. The fog lifted, space became transparent, and light, at last, was free to journey across the cosmos. That ancient light still fills the universe today. We call it the cosmic microwave background. It has been traveling for over 13 billion years, stretched by cosmic expansion into faint microwaves. It's not light from stars or galaxies. It's light from the universe itself, a quiet echo of its early transformation. When scientists map this background glow, they're reading a fossil imprint of the cosmos as it was in its infancy, a baby picture of everything. The universe is not only vast, it is wildly diverse. In some distant systems, planets may be made of materials that sound almost mythical. Consider a world formed in a region rich in carbon. Under immense pressures, carbon atoms can crystallize into diamond. Astronomers have identified at least one compelling candidate: a dense exoplanet orbiting a pulsar, likely the remnant core of a once massive star. Based on its mass and density, researchers suspect it could be composed largely of crystalline carbon, a planet-scale diamond. It wouldn't sparkle like a gemstone in a jewelry store. The surface would be unimaginably hostile, heated and bombarded by radiation. But deep within, vast carbon lattices could stretch for thousands of kilometers. Rocky worlds, gas giants, ice planets, and perhaps in rare cases, crystal ones. The cosmos seems to explore every chemical possibility. Now let's think about the shape of everything. It's natural to imagine the universe having an edge, a boundary we could reach if we traveled far enough. But according to general relativity, space doesn't necessarily have an edge at all. Its geometry depends on its overall mass and energy. Current measurements suggest that the universe is very close to spatially flat. That could mean it extends infinitely, or it could mean it's curved so gently that its full shape lies beyond what we can observe. In some geometries, space could loop back on itself. If that were true, traveling in a perfectly straight line for long enough might eventually bring you back to your starting point, not by hitting a wall, but by following the curvature of space itself, much like walking around Earth without ever encountering an edge. It's not infinite in the sense of empty void beyond a border. It may simply be self-contained, without boundary. Endless, not because it has no shape, but because its shape never ends. And then there's our own sun. Evidence suggests that most stars form in clusters, born from collapsing clouds of gas and dust. It's entirely possible that our sun once had a stellar sibling, a twin formed from the same molecular cloud over 4.5 billion years ago. Over time, gravitational interactions within their birth cluster may have separated them, sending each star on its own orbit around the Milky Way. If that sibling still exists, it could be anywhere in the galaxy by now, indistinguishable from countless other stars. We may never know which one it is. Somewhere out there, perhaps, a star shares our origin story, a distant relative, shining under a different sky. As we drift here at the edge of this chapter, consider how much of the universe remains unseen. Rogue worlds wander in darkness. Ancient light whispers from a time before stars. Space itself may curve in ways we cannot directly perceive. And our sun may once have had a companion we've long since lost. The more we learn, the more gently the mystery expands. And maybe that's the most comforting part. We are not standing at the end of knowledge. We are floating within it. Before we continue, here's something to ponder. If you could visit one of these cosmic mysteries, a rogue planet, a diamond world, or the moment the universe first became transparent, which would you choose and why? Let that question drift with you as we move deeper into the stars. Chapter 2: Strange Worlds. There's a quiet possibility hidden in our own origin story. Most stars are not born alone. When vast clouds of gas collapse to form new suns, they often fragment, creating pairs or even trios of stars bound together by gravity. Binary systems are common throughout the Milky Way, so it's reasonable to wonder whether our sun once had a sibling, a companion formed from the same swirling cradle of dust more than 4.5 billion years ago. If such a twin existed, it would not be nearby now. The Sun was born in a crowded stellar nursery, where gravitational nudges from neighboring stars slowly reshuffled the family. Over millions of years, siblings drifted apart, captured into new galactic orbits. Our Sun's hypothetical twin, sometimes nicknamed Nemesis in speculative theories, would by now be indistinguishable from countless other stars circling the Milky Way. At one time, some researchers wondered whether a distant companion could have triggered periodic comet showers and mass extinctions on Earth. But no convincing evidence has ever supported that claim. Still, the idea lingers. The calm, solitary star in our sky may once have shared its beginning with another light, now long separated by time and gravity. If that thought feels expansive, consider something far denser. When a massive star reaches the end of its life, it can explode in a supernova, leaving behind a collapsed core known as a neutron star. These objects are astonishingly small, typically only about 20 kilometers across, yet they can contain more mass than our entire Sun. Imagine compressing a star's worth of material into a sphere roughly the size of a city. Inside a neutron star, matter exists in a form that challenges comprehension. The gravitational pressure is so extreme that electrons and protons are forced together, merging into neutrons. The result is a vast sphere of tightly packed particles, something like a single atomic nucleus scaled up to planetary size. A teaspoon of neutron star material would weigh billions of tons. Even a droplet the size of a raindrop would outweigh Mount Everest. These stars often spin rapidly, some rotating hundreds of times per second, emitting beams of radiation like cosmic lighthouses. Yet despite their violence and speed, they are also monuments to stillness, final remnants of stellar collapse where matter has been pushed almost to its absolute limit. And gravity does more than crush stars. It bends light itself. In regions where gravity is especially strong, around massive galaxy clusters, for example, space and time curve in response. When light from a distant galaxy passes through this curved region, its path bends. This phenomenon, predicted by Einstein's general relativity, is called gravitational lensing. Sometimes the effect is subtle, slightly stretching a distant galaxy into a faint arc. In rarer cases, it creates luminous rings known as Einstein rings, where a background galaxy appears wrapped into a circle by the gravity of a foreground mass. Even more remarkable, the same object can appear multiple times in the sky. Its light has traveled along different routes through warped space-time, arriving at Earth from separate directions. There have even been instances where astronomers observed a single supernova more than once. The explosion happened only once, but its light took multiple paths, arriving at different times. It's a gentle reminder that in the universe, even light can wander, delayed by the curves of invisible gravity, and still find its way to us. Long before galaxies matured into their present forms, the very first stars ignited. These primordial stars, known as population 3 stars, were born from pristine hydrogen and helium left over from the Big Bang. Unlike modern stars, they contained virtually no heavier elements. Without those elements to regulate their internal structure, many of these early stars likely grew to enormous sizes, perhaps hundreds of times the mass of our Sun. They burned fiercely and briefly. Some may have shone 1,000,000 times brighter than the Sun, flooding the young universe with ultraviolet light. But their lives were short, lasting only a few million years before collapsing in titanic explosions. In those final moments, they forged the first heavy elements: carbon, oxygen, iron, the building blocks of planets and people. None of these first stars survive today, but their chemical fingerprints remain scattered in ancient gas clouds and embedded in the oldest surviving stars. Every atom of calcium in your bones and iron in your blood can trace its ancestry back to such stellar furnaces. In that sense, their light never truly disappeared. And while visible matter tells one story, something unseen shapes the cosmos even more profoundly. As you sit or lie here, dark matter is flowing silently through you. It does not glow, it does not absorb light, it does not reflect it, yet it possesses mass and it exerts gravity. Astronomers infer its presence because galaxies rotate too quickly to be held together by visible matter alone. Without an unseen gravitational scaffold, stars at the edges of galaxies would drift away. Our Milky Way is embedded in a vast halo of dark matter extending far beyond its luminous disk. As Earth orbits the Sun, and as the Sun orbits the galaxy, we move through this halo. Trillions of dark matter particles likely pass through your body every second. They do not collide with your atoms in any noticeable way. They leave no warmth, no sensation. But without them, galaxies as we know them would never have formed. We still don't know what dark matter is made of. It remains one of the greatest mysteries in modern physics. Yet it is not distant. It is here, woven quietly into the structure of your world. And then there are galaxies that seem almost reluctant to shine. Astronomers have discovered faint systems sometimes called ultra-diffuse galaxies, large in size but containing surprisingly few stars. Some appear rich in dark matter yet poor in visible light. Others may have lost much of their gas through violent gravitational encounters, halting star formation before it could truly begin. These ghostly galaxies challenge our understanding of how galaxies grow. If dark matter provides the gravitational foundation for star formation, why do some systems remain so dim? Did they fail to ignite, or were their stars stripped away long ago? In deep sky surveys, they appear as barely perceptible smudges, cosmic phantoms drifting in silence. Even the afterglow of the Big Bang contains puzzles. When scientists map the cosmic microwave background, the faint radiation left over from the early universe, they find it remarkably uniform. But there is one region, known as the cold spot, that stands out. It spans a vast area of sky and is significantly cooler than surrounding regions. Some researchers suggest it may be caused by a gigantic cosmic void, an enormous region with fewer galaxies than average. As light passes through such a void, it can lose a small amount of energy. Others have speculated more boldly about exotic explanations involving early universe physics. So far, no single explanation fully accounts for its features. The cold spot remains a quiet anomaly, subtle, not dramatic, but persistent. It's not a glaring tear in our cosmological model. It's more like a faint smudge on the edge of certainty. And closer to home, even our nearest companion is slowly drifting away. The Moon is receding from Earth at a rate of about 3.8 centimeters per year. This happens because tidal interactions transfer rotational energy from Earth to the Moon, nudging it into a slightly higher orbit. Over millions of years, this process has lengthened our days and widened the distance between us. Billions of years from now, total solar eclipses as we know them will no longer occur. The Moon will appear slightly smaller in the sky, no longer perfectly covering the Sun. The relationship between Earth and Moon, so steady and familiar, is quietly evolving. Across all these scales, from vanishing star siblings to collapsing neutron cores, from ghost galaxies to drifting moons, the universe reveals itself as both dynamic and delicate. Nothing is entirely fixed. Even light bends. Even gravity reshapes the path of time. As we pause at the edge of this chapter, consider how many unseen forces shape your existence at this very moment. Ancient stellar explosions that forged your atoms, dark matter holding galaxies together, the Moon slowly widening its orbit, and perhaps a long-lost stellar twin orbiting somewhere in the Milky Way. The cosmos is not just out there. It is threaded through your story. And here's a small question to carry with you. If you could witness one of these phenomena up close, a neutron star spinning in darkness, a galaxy split into multiple images by gravity, or the birth of the first star, which would you choose to see? Chapter 3. The First Light. If you hold your hand still and look at your fingernails, you might not notice them changing, but over weeks, you'll see the quiet evidence of growth. That slow, almost invisible pace, just a few centimeters per year, is roughly how fast the Moon is drifting away from Earth. About 3.8 centimeters each year. Barely the width of 2 stacked coins. This gradual retreat has been unfolding for over 4.5 billion years, ever since the Moon formed in the aftermath of a colossal collision between the young Earth and a Mars-sized body. In those early days, the moon loomed far larger in the sky. It orbited much closer, and Earth spun far faster. A single day may have lasted only 5 or 6 hours. The reason for this steady separation is tidal friction. The moon's gravity pulls on Earth's oceans, raising tidal bulges. As Earth rotates, those bulges are dragged slightly ahead of the moon's position. That offset creates a gravitational tug, transferring rotational energy from Earth to the moon. Our planet's spin slows ever so slightly, and the moon gains energy, moving into a higher orbit. It is a patient exchange. Earth's days lengthen. The moon slips farther away. Billions of years from now, if both bodies survive the sun's evolution, they may become tidally locked to each other, each always showing the same face to the other, suspended in a mutual gaze. For now, though, we spin beneath its familiar glow, unaware that the distance between us is quietly widening. But distance is only one kind of cosmic relationship. Some stars live in far more intimate arrangements. In close binary systems, two stars orbit one another so tightly that as they age and swell, their outer layers can begin to touch. When this happens, matter may flow from one star to the other in a spiraling stream, forming luminous disks of gas. Sometimes this transfer is gentle, a steady siphoning that alters both stars over millions of years. Other times, the exchange becomes unstable, triggering sudden flares of brightness or even catastrophic explosions. One star may be stripped down to its exposed core, becoming a white dwarf. The other may grow bloated and luminous, enriched by stolen material. In certain cases, these systems eventually produce rare phenomena, type Ia supernovae, neutron star pairs, or gravitational wave events when compact remnants finally collide. It's a strangely graceful image, two stars circling so closely that they share substance, reshaping one another's fate. In the vastness of space, even stars can exchange gifts and consequences, and even in the emptiest places between them, the universe is not truly empty. When we imagine deep space, we often picture a perfect vacuum, silent, still, nothing at all. But quantum physics tells a different story. What we call empty space is alive with fluctuations. At unimaginably small scales, particle-antiparticle pairs briefly flicker into existence and then vanish, borrowing energy from the vacuum and returning it almost instantly. These quantum fluctuations happen everywhere, all the time. They are subtle and normally undetectable in daily life, yet they form a restless background to reality itself. Some physicists believe that the energy of this vacuum may be related to dark energy, the mysterious phenomenon causing the expansion of the universe to accelerate. So, beneath the apparent stillness of intergalactic space, there is a quiet turbulence. Not chaos in the ordinary sense, but a constant shimmering of probabilities. Even nothingness hums. And if space can be restless, so too can time. We tend to think of time as steady and universal, a shared rhythm ticking evenly throughout the cosmos. But according to Einstein's theory of relativity, time is intertwined with space and gravity. Near massive objects, such as black holes or dense galaxy clusters, gravity curves space-time so strongly that time itself slows down relative to regions with weaker gravity. This effect is not merely theoretical. It has been measured using atomic clocks on satellites and airplanes. Even GPS systems must account for gravitational time dilation to function accurately. Some cosmologists have explored whether time might also vary on grander cosmic scales. Could different regions of the early universe have expanded at slightly different rates, subtly influencing how time unfolded across vast distances? These ideas remain speculative, but they remind us that time is not an absolute river flowing identically everywhere. It bends, it stretches, it responds to the shape of the cosmos. In a universe governed by relativity, even the passage of seconds is shaped by gravity's quiet hand. Now imagine stepping far outside our galaxy and looking back. The Milky Way appears to us as a luminous spiral disk of stars, dust, and glowing nebulae. But this visible structure is only the bright center of something much larger. Surrounding it is a vast galactic halo, a roughly spherical region extending hundreds of thousands of light-years beyond the disk. This halo contains ancient globular clusters, sparse gas, and, most importantly, enormous amounts of dark matter. Though invisible, this dark matter provides much of the gravitational glue that holds the galaxy together. Without it, the outer stars would drift away into intergalactic space. The Milky Way is not merely a flat spiral. It is a glowing heart wrapped in an immense, unseen envelope. What we see is only a fraction of what exists. And when we look even farther, back in time itself, we glimpse the first sparks of structure. Thanks to the James Webb Space Telescope, astronomers have detected light from galaxies that formed astonishingly early in cosmic history, just about 200 million years after the Big Bang. On the scale of a 13.8 billion-year-old universe, that is the briefest flicker of time. The light from these primitive galaxies has been traveling toward us for more than 13.5 billion years, stretched into infrared wavelengths by the expansion of space. These galaxies are small and chemically simple, composed mostly of hydrogen and helium. Yet within them, the first generations of stars were already igniting, ending the cosmic dark ages. To observe such distant objects is to peer through a narrow keyhole into the universe's childhood. We are not seeing them as they are now, but as they were when the cosmos was still learning how to shine. And when astronomers map the positions of galaxies across billions of light years, a remarkable pattern emerges. Galaxies are not randomly scattered. Instead, they gather along vast filaments, forming an immense interconnected structure known as the cosmic web. Between these filaments lie enormous voids, regions nearly empty of galaxies. The result resembles a three-dimensional network, threads of light and matter woven across the observable universe. Strikingly, when visualized on large scales, this cosmic web bears an uncanny resemblance to neural networks in the human brain. Dense clusters of galaxies resemble nodes, while the filaments stretch between them like connections. The similarity is structural, not functional. The universe is not thinking in any literal sense, but the visual echo is difficult to ignore. On the largest scales we can observe, matter arranges itself in patterns that feel almost organic. From the moon's gentle retreat to stars exchanging their outer layers, from quantum fluctuations in empty space to galaxies forming a cosmic web, the universe reveals itself as deeply interconnected. Motion and structure, time and gravity, light and darkness, all woven together in ways both measurable and mysterious. As we rest at the close of this chapter, consider how many layers of reality operate beyond everyday perception. The moon drifts outward. Time bends near massive objects. Invisible halos cradle galaxies. And ancient light from the first galaxies continues to arrive, whispering stories from a time before Earth existed. Here's something to ponder as you drift onward. If the cosmic web resembles a neural network, what do you think that resemblance says about the patterns that nature prefers to build? Let that question settle gently in your mind as we continue deeper into the first light. Chapter 4. The Hidden Structures. When astronomers first mapped the large-scale structure of the universe, they noticed something uncanny. On the grandest scales, galaxies arrange themselves in filaments and nodes, forming a vast interconnected web. When compared visually to a neural network inside the human brain, the resemblance is striking. Two systems shaped by entirely different forces, gravity on one hand, biology and chemistry on the other, yet both produce branching networks of connection. The universe is not thinking. It has no awareness in the way a brain does, and yet it is quietly beautiful to realize that patterns repeat across scales. Nature seems to favor certain architectures, threads, clusters, intersections. From neurons to galaxies, structure emerges from simple rules applied over immense spans of time. But while galaxies form networks across billions of light years, stars have their own hidden lives much closer to home. Space is often imagined as silent, and in one sense it is. Sound, as we experience it on Earth, requires air or some medium to carry vibrations to our ears. The vacuum between stars cannot transmit sound in that familiar way. Yet inside a star, there is no silence at all. Within the roiling plasma of a star, pressure waves ripple outward and inward, bouncing between layers of different density. These waves cause the star to subtly expand and contract, to oscillate in complex rhythms. The changes are tiny, variations in brightness or surface motion so slight that they require extraordinarily sensitive instruments to detect, but they are measurable. The study of these stellar vibrations is called astroseismology. By analyzing a star's frequencies, its internal resonances, scientists can determine its size, mass, age, and even aspects of its internal structure. Each star has its own set of tones, like a fingerprint encoded in vibration. We cannot hear these sounds with our ears. Many of them are far below the range of human hearing. But when converted into audio frequencies, they reveal deep, haunting pulses. In a sense, stars sing, not in melody or harmony as we know it, but in oscillations governed by gravity and thermodynamics. Across light years of vacuum, we have learned how to listen. Our own star, the Sun, is no exception. Deep within its interior, sound waves travel through hot plasma, reflecting and refracting through layers of differing temperature and density. This field of study, heliosismology, has allowed scientists to map the Sun's internal rotation, convection currents, and hidden flows of energy. The Sun behaves like a vast resonant instrument, continuously ringing with low, booming vibrations. It is not static. It is dynamic and alive with motion beneath its surface. By understanding how our Sun oscillates, we refine our knowledge of stellar physics everywhere. And yet some stars are older than the galaxies they now inhabit. Galaxies do not form all at once. They grow gradually, assembling themselves through mergers and acquisitions. Smaller galaxies collide and blend into larger ones, carrying their stars with them. As a result, a galaxy's current structure may be younger than some of the stars within it. In the outskirts of galaxies, particularly within ancient globular clusters, astronomers find stars that are more than 13 billion years old, nearly as old as the universe itself. These stars formed when the cosmos contained almost nothing but hydrogen and helium. Heavy elements were scarce. Their chemical composition preserves the memory of a younger universe. They are stellar fossils, survivors from an earlier cosmic epoch. Long before spiral arms fully formed or galactic disks settled into shape, these stars were already shining. If galaxies are shaped by mergers, they are also shaped by something far more mysterious: dark matter. Dark matter forms an invisible scaffolding across the universe. Over billions of years, it collapsed under its own gravity into enormous filaments, stretching across hundreds of millions of light years. Ordinary matter, gas and dust, fell into these gravitational wells, eventually forming galaxies along the filaments like beads threaded on cosmic strings. Between these filaments lie immense voids, regions where very little matter exists. The visible universe, stars, nebulae, glowing galaxies, traces out this hidden architecture. We cannot see the dark matter directly, but we observe its gravitational influence in the motion of galaxies and in the bending of light. And yet, in recent years, astronomers have identified a handful of galaxies that appear to contain little to no dark matter at all. Their stars move as if only visible matter is present. This discovery challenges conventional models. Perhaps their dark matter was stripped away in violent encounters. Perhaps our understanding remains incomplete. The cosmic scaffolding seems universal until it isn't. Even the expansion of the universe itself reveals hidden structures in motion. We often hear that nothing can travel faster than light. That is true for objects moving through space, but space itself can expand without that limitation. In the earliest fraction of a second after the Big Bang, during a period known as inflation, space expanded so rapidly that distant regions were carried apart faster than light could travel between them. This was not a violation of relativity. It was the stretching of space itself. Even today, galaxies far enough from us are receding faster than light, not because they are speeding through space, but because the fabric between us and them is expanding. Their light will never reach us. There are parts of the universe that are permanently beyond our observational horizon. The expansion is calm, relentless, and ongoing. And closer to home, motion is just as constant. We tend to picture the solar system as a tidy arrangement, planets tracing flat, elliptical paths around a stationary sun. But the sun is not stationary. It orbits the center of the Milky Way at roughly 220 kilometers per second, about 800,000 kilometers per hour. As it moves, the planets follow, not merely circling the sun, but spiraling through the galaxy. The result is not a stack of flat circles, but a graceful, helical pattern, a corkscrew motion through space. Earth is never retracing the same path. Each orbit around the sun occurs in a new region of the galaxy. Nothing is still. Not the planets, not the sun, not the galaxy. Everything drifts in layered motion. From singing stars to invisible filaments, from ancient stellar fossils to galaxies that defy expectations, the universe reveals itself as a tapestry of hidden structures. Some are vast beyond imagination. Others are subtle vibrations inside a single star. Together, they form a cosmos that is dynamic, interconnected, and far more intricate than it first appears. As we pause here, consider how much of reality lies beneath surfaces. Beneath the sun's bright face, it rings. Beneath galaxies' glow, dark matter binds them. Beneath the apparent stillness of space, expansion reshapes distances. And beneath our own perception, patterns repeat across scales, from neurons to galaxy clusters. Here's a gentle question to carry forward. If you could hear one celestial sound, the deep pulse of the sun, the oscillation of a distant star, or the gravitational whisper of merging galaxies, which would you choose to listen to? The universe may not be thinking, but it is always moving, always resonating, and always quietly revealing its hidden structures. Chapter 5. The Cosmic Web. Even as you rest, eyes closed and body still, you are in motion. Earth turns beneath you. It circles the sun. The sun arcs around the center of the Milky Way, and the Milky Way itself drifts through a larger cosmic current shaped by distant structures we cannot see with the naked eye. Orbits within orbits, spirals within spirals. A choreography so immense and gradual that it feels like stillness. And yet, even in the deepest stillness imaginable, there is warmth. If you could travel far beyond the stars, past galaxies, past clusters, into the wide gulfs of intergalactic space, you might expect to find absolute emptiness. But the vacuum of the universe is not truly cold in the way we define absolute zero. It carries a faint temperature, about 2.7 Kelvin, just a few degrees above the coldest temperature physically possible. That gentle warmth comes from the cosmic microwave background, the afterglow of the Big Bang. Nearly 13.8 billion years ago, when the universe first became transparent, light began its long journey outward. Over billions of years, as space expanded, that light stretched into microwaves and cooled dramatically. Yet it never vanished. No matter where you travel in the observable universe, this faint radiation surrounds you. It is the thermal memory of creation itself, a quiet echo. And as the universe continues to expand, that background glow will cool further. In trillions upon trillions of years, it may approach absolute zero, but it will never quite reach it. Even nothing carries a trace of heat, and even nothing once trembled. At the smallest conceivable scales, far smaller than atoms, the universe is governed by quantum uncertainty. Tiny fluctuations in energy constantly flicker into and out of existence. These events are random and fleeting, normally confined to subatomic scales. But in the earliest fraction of a second after the Big Bang, during a period known as cosmic inflation, space expanded at an extraordinary rate. In that explosive growth, microscopic quantum fluctuations were stretched to cosmic dimensions. What began as minute ripples in energy became slight variations in density across vast regions of space. Over time, gravity amplified those variations. Matter flowed toward denser regions, forming clouds, then stars, then galaxies. The immense filaments and voids we see today may ultimately trace their origins back to those tiny quantum tremors. The largest structures in existence, clusters spanning hundreds of millions of light-years, may owe their beginnings to fluctuations smaller than a proton. From trembling nothingness, the cosmic web was born. Within that web, stars live out lifetimes of astonishing variety. Some depart in brilliant explosions, others fade more gently. There are stars known as variable stars that swell and contract in steady rhythms, their brightness rising and falling like a slow heartbeat. These pulsations are caused by cycles in their outer layers. Gases heat, expand, cool, and fall inward again, repeating the process over days, months, or even years. Certain types of variable stars, such as Cepheid variables, have been crucial to astronomy. Their pulsation periods are directly related to their intrinsic brightness, allowing astronomers to measure distances across the galaxy and beyond. In this way, dying stars have helped us map the scale of the universe. Even in decline, they keep time, not with ticking seconds, but with luminous breaths stretching across space. Meanwhile, our own solar system drifts through the aftermath of ancient violence. We reside within a region called the local bubble, a vast cavity of hot, low-density gas extending for hundreds of light-years. This bubble was likely carved out by multiple supernova explosions millions of years ago. Shock waves from those blasts swept away surrounding material, heating and clearing the region. Today, our sun glides quietly through this sparse chamber, unaware of the long-ago cataclysms that shaped it. The violence has faded. What remains is a gentle backdrop, a hollowed-out pocket within the Milky Way. We float inside a relic of stellar death, now calm and nearly invisible. And on even larger scales, our galaxy itself is being guided by both presence and absence. Astronomers have long studied a region known as the Great Attractor, a massive concentration of galaxies exerting a gravitational pull on our local group, including the Milky Way. Though obscured by dust and gas in our line of sight, its gravitational influence is unmistakable. Entire galaxy clusters drift slowly toward it. But opposite this immense mass lies something equally influential, a vast cosmic void sometimes referred to as the dipole repeller. It is not that emptiness exerts a force in the usual sense. Rather, regions with less mass exert less gravitational pull, effectively allowing surrounding matter to move away more easily. In combination, the dense great attractor and the sparse void behind it shape the motion of galaxies in our region of the universe. We are drawn forward by hidden mass and shaped by surrounding emptiness. Both matter and void guide our path. And while galaxies drift and gravity molds the cosmic landscape, particles pass through you right now, unnoticed. Neutrinos, nearly massless, electrically neutral particles, are produced in staggering numbers by the sun, by supernovae, and by processes that occurred in the early universe. Trillions of them pass through your body every second. They travel at nearly the speed of light, interacting so weakly with matter that most will pass through the entire Earth without colliding with a single atom. Deep underground detectors occasionally capture the rare flash of a neutrino interaction, offering insight into nuclear processes inside stars and beyond. But most neutrinos continue on silently, ghost-like, indifferent to planets, oceans, or human bodies. Motion everywhere. Interaction almost nowhere. And sometimes, when a massive star reaches the end of its life, there is no dramatic farewell at all. We often imagine stellar death as a brilliant supernova, a burst of light briefly outshining entire galaxies. But for the most massive stars, the end can be unexpectedly quiet. If the star's core is heavy enough, gravity may overwhelm all opposing forces so completely that the entire structure collapses inward. The outer layers fall straight into the core. No explosive rebound, no luminous display, the star simply disappears. In its place remains a black hole, an object so dense that not even light can escape its grasp. Astronomers have observed candidates for such failed supernovae, stars that seem to fade from view without the expected flash, a light extinguished without announcement. Across the cosmic web, from quantum ripples to galaxy clusters, from silent neutrinos to vanishing stars, the universe is a study in contrasts. Immense structures born from microscopic fluctuations, warmth lingering in emptiness, motion within stillness, gravity shaped by both mass and void. As you lie here, spiraling gently through space, wrapped in layers of invisible influence, consider how much of reality unfolds beyond perception: heat in the vacuum, particles through your skin, galaxies tugged by unseen giants, stars collapsing without a sound. Here's a quiet thought to leave you with. If the entire large-scale structure of the universe began as tiny quantum fluctuations, what small, almost invisible beginnings around us today might one day grow into something vast? The cosmic web stretches outward, silent and immense, and we drift within it, part of its pattern, whether we feel it or not. Chapter 6. Motion Everywhere. When we picture the universe, it's easy to imagine stillness, a frozen tapestry of stars pinned against a dark canvas. But nothing out there is truly at rest. Every galaxy, every star, every atom is in motion, tracing paths so vast and slow that to us, they feel like permanence. Take our own galaxy. The Milky Way is not a solitary island drifting in isolation. It lives in a small gravitational family known as the local group, surrounded by dozens of smaller companion galaxies. Two of the most visible are the Large and Small Magellanic Clouds, faint smudges of light visible from the southern hemisphere. They are not merely background ornaments. They are satellite galaxies, gravitationally bound to the Milky Way, orbiting it the way moons circle a planet, though on scales that stretch across hundreds of thousands of light years. Over immense stretches of time, these companions are gently tugged and reshaped by our galaxy's gravity. Long streams of stars, tidal tails, are pulled from them like cosmic ribbons, stretching across space in luminous arcs. Eventually, some of these smaller galaxies will be absorbed entirely, their stars folded into the Milky Way's spiral arms. These interactions are not violent crashes in the cinematic sense. They are slow gravitational conversations, unfolding over billions of years. In the deep quiet of space, even galaxies keep each other company. But while some cosmic motions are graceful, others are explosive beyond comprehension. At the end of certain massive stars, the collapse does not simply produce a supernova. Under rare and extreme conditions, the collapsing core can form a magnetar, a type of neutron star with a magnetic field so powerful it defies ordinary imagination. A magnetar's magnetic strength can be trillions of times greater than Earth's, warping atoms themselves. If such an object forms rapidly and releases its rotational energy in a short burst, it can power what astronomers call a hypernova. These are among the brightest explosions in the universe. Some of the most intense, long-duration gamma-ray bursts, flashes of high-energy radiation that briefly outshine entire galaxies, are thought to arise from these catastrophic births. For a few seconds, an unimaginable torrent of energy is unleashed, and yet that flash can travel billions of light years, eventually reaching telescopes on a quiet planet orbiting an ordinary star. A brief cosmic heartbeat echoing across nearly all of time. And still, even with all this brilliance, there are limits to what we can see. When astronomers speak of the edge of the universe, they aren't describing a wall or a boundary. They are referring to the edge of the observable universe, the farthest distance light has had time to reach us since the Big Bang. Because space itself has been expanding, that distance is now about 46 billion light years in every direction. It forms a kind of cosmic horizon, a bubble centered on us. Not because we are special, but because we can only observe from where we stand. Beyond that horizon, the universe almost certainly continues. There may be more galaxies, more clusters, perhaps infinitely more space. But due to the accelerating expansion driven by dark energy, some regions are receding from us faster than light. Their future light will never reach Earth, no matter how long we wait. There are parts of reality forever beyond our view. The observable universe is not all that exists. It is simply the portion available to our story. Within that visible realm, some galaxies announce themselves with astonishing displays. At the center of many large galaxies lies a supermassive black hole. When matter spirals toward one of these gravitational giants, it forms a swirling disk heated to extreme temperatures. Not all of this matter crosses the event horizon. Some of it becomes trapped in powerful magnetic fields and is redirected outward in twin jets, narrow beams of plasma accelerated to near the speed of light. These jets can extend for millions of light years, far beyond the visible structure of their host galaxies. In radio wavelengths, they glow like colossal searchlights, terminating in vast lobes where the jets slam into surrounding intergalactic gas. Such systems are known as radio galaxies, and their jets rank among the largest coherent structures in the cosmos. It is a strange paradox. From regions defined by darkness and inescapability, we witness some of the most powerful outflows in existence. Not all motions follow the general flow, however. Most stars in the Milky Way orbit the galactic center in roughly the same direction, following the overall rotation of the galaxy. Yet astronomers have identified rare exceptions: stars moving on retrograde orbits, traveling against the dominant galactic current. One such star, cataloged as J0437Plo2456, appears to move in the opposite direction from most of its neighbors. How does a star end up swimming upstream in a galaxy-wide river? One explanation is galactic archaeology. Our Milky Way has merged with smaller galaxies in the past. A star born in one of those ancient systems may retain the orbital motion of its original home, even after being assimilated. Another possibility involves gravitational slingshots, where interactions with dense star clusters or black holes alter a star's trajectory dramatically. Whatever the cause, these stellar rebels remind us that even in a system governed by gravity's steady rules, there is room for deviation. Then there are the quieter, more unexpected details of our galaxy. Near the center of the Milky Way, astronomers have detected a molecule called ethyl formate within dense molecular clouds. On Earth, this compound contributes to the flavor of raspberries and the scent of rum. Of course, space itself does not carry smells. There is no air to transport scent to a nose, but the chemistry is real. Interstellar clouds contain alcohols, sugars, and even molecules that are precursors to amino acids. This does not mean the galactic center smells like a cocktail bar, but it does hint at something profound. The building blocks of complex chemistry are widespread. The ingredients for life, or at least for the chemistry that can lead to life, drift quietly between the stars. Motion here is not just about stars and galaxies. It is about molecules forming, reacting, and evolving across cold cosmic clouds. And perhaps the grandest motion of all is one already underway. The Andromeda Galaxy, our nearest large galactic neighbor, lies about 2.5 million light-years away. It is not stationary relative to us. It is moving closer at roughly 110 kilometers per second. In about 4 billion years, the Milky Way and Andromeda will begin to merge. But the process has, in a subtle sense, already begun. The vast halos of dark matter and hot gas surrounding both galaxies are thought to be overlapping even now. The eventual merger will not be a catastrophic collision of stars. Space within galaxies is so vast that direct stellar collisions are rare. Instead, the two spirals will interweave, their structures distorted by gravity, eventually settling into a single, larger, elliptical galaxy, sometimes nicknamed Milkomeda. This is not a sudden event. It is a slow gravitational ballet unfolding over billions of years. Entire constellations will rearrange. The night sky, as seen from Earth, if Earth still exists, will be transformed into something unrecognizable. Everywhere we look, motion defines the universe. Galaxies orbit one another. Black holes launch jets. Stars rebel against rotation. Molecules assemble in dark clouds. Even the horizon of our observable universe is shaped by expansion itself. What feels stable and eternal is, in truth, dynamic and evolving beyond our everyday perception. The cosmos is not a static painting. It is a process, ongoing, restless, and deeply interconnected. And perhaps that is the most humbling thought of all. While we sit still and listen, we are already part of countless motions we cannot feel. Here's a light question to leave you with. Which galaxy is currently on a collision course with the Milky Way? And roughly how many billion years from now will the merger begin? Chapter 7. Our Local Bubble. Right now, as you sit wherever you are, in a quiet room, under city lights, or beneath an open night sky, you are immersed in ancient light. It does not glow visibly, it does not warm your skin, and yet it fills every direction around you. This faint radiation is known as the cosmic microwave background. It is the afterglow of the Big Bang, released when the universe was about 380,000 years old. Not 380 million, but 380,000. In those earliest moments, the cosmos was not filled with stars or galaxies. It was a dense, blinding plasma of charged particles and light, tangled together so tightly that photons could not travel freely. The universe was opaque, like a glowing fog. Then, as expansion continued, everything cooled. Protons and electrons combined to form the first neutral hydrogen atoms. With fewer charged particles to scatter them, photons were suddenly free to move unimpeded. The universe became transparent. That ancient light began its journey across space. And it has never stopped. Over billions of years, as space itself stretched, the wavelength of that radiation stretched too. What was once visible light has been redshifted into microwaves, corresponding to a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. Sensitive instruments aboard satellites have mapped this glow across the entire sky. It is nearly uniform, with tiny fluctuations that seeded galaxies. It is the oldest light we can see, a quiet photograph of the universe in its infancy. And beyond that faint glow, in the vast emptiness between galaxies, the cold deepens. Intergalactic space is colder than almost any environment we can create on Earth. In the great cosmic voids, enormous regions spanning millions of light years with very few galaxies, the temperature hovers only slightly above that 2.7 Kelvin background. There are almost no particles to hold heat, just a few stray atoms per cubic meter and the faint microwave whisper of creation itself. These voids are the most silent places we know. No starlight illuminates them directly. No dense gas clouds drift through them. They are the universe's deepest shadows, enormous, expanding, and nearly empty. Yet even in these cold regions, drama unfolds elsewhere in ways we cannot see with ordinary eyes. When we think of supernovae, we imagine brilliant explosions, stars flaring so brightly they briefly outshine entire galaxies. And indeed, many do. But not all stellar deaths are luminous spectacles. Some are far more secretive. In certain massive stars, when nuclear fusion can no longer support the core against gravity, collapse happens so completely that the energy needed to power a bright explosion never reaches the surface. The core implodes, forming a black hole, and the outer layers fall inward rather than blasting outward. Astronomers sometimes call these events failed supernovae. In recent years, telescopes have observed massive stars that simply vanished. They appeared stable. Then, without warning, they were gone. No bright explosion, no fading remnant, just absence. The violence still occurred, but most of it was swallowed behind an event horizon, a cosmic death hidden from view. Black holes, once formed, do not remain isolated forever. Sometimes two of them find each other in orbit. As they circle, they emit gravitational waves, ripples in spacetime predicted by Albert Einstein a century ago in his theory of general relativity. These waves carry energy away from the system. Slowly, the black holes spiral closer and closer together, until in a fraction of a second, they merge. The collision produces no flash of light if no surrounding matter is present. But it releases an astonishing amount of energy in gravitational waves, sometimes equivalent to several times the mass of our sun converted directly into pure energy. In 2015, detectors on Earth recorded the first such signal. The fabric of spacetime itself had trembled. Since then, dozens more mergers have been detected, each one a silent but powerful echo from distant galaxies. And gravity's influence does not stop at waves. It alters time itself. According to general relativity, gravity is not simply a force pulling objects together. It is the curvature of space-time. The stronger the gravitational field, the more space and time are warped. Near a black hole, this effect becomes extreme. If you were to orbit just outside the event horizon, close enough to feel the full strength of its gravity but not fall in, time for you would slow dramatically compared to a distant observer. Minutes in that intense gravitational field could correspond to years far away. This phenomenon, called gravitational time dilation, has been experimentally confirmed in weaker gravitational fields. Even GPS satellites must account for it to maintain accuracy. Near a black hole, the effect becomes profound. Black holes do not merely trap light, they stretch time. Meanwhile, not all galaxies shine brightly enough to announce their presence. Some galaxies contain very few stars at all. They are composed largely of gas and dark matter, with only a sparse sprinkling of visible light. These dim systems are difficult to detect, often discovered indirectly through their gravitational influence. Some may be galaxies that never formed many stars because their gas was stripped away or heated too early in cosmic history. Others may represent transitional phases. They do not blaze with spiral arms or glowing cores. They simply exist. Quiet reservoirs of mass in a universe where brightness is not required for presence. And then there are stars like our own sun, destined for a quieter fate than explosive collapse. In about 5 billion years, the sun will exhaust the hydrogen in its core and swell into a red giant. It will shed its outer layers gently into space, creating a glowing shell of gas known as a planetary nebula. What remains at the center will be a white dwarf, a dense, Earth-sized ember composed mostly of carbon and oxygen. A white dwarf no longer generates energy through fusion. It shines only from residual heat, cooling gradually over billions of years. In theory, given enough time, far more time than the universe has yet existed, a white dwarf would cool into a black dwarf, a cold, dark remnant. But the cosmos is only about 13.8 billion years old. No black dwarfs exist yet. Every white dwarf ever formed is still glowing faintly somewhere in the dark. All of this unfolds within our galactic neighborhood, including the region known as the local bubble. Our solar system resides inside a vast cavity of low-density hot gas extending hundreds of light-years across. It was likely carved out by ancient supernovae that exploded millions of years ago, sweeping away surrounding material. Today, we drift quietly within this bubble, a remnant of long-ago stellar violence. And as the universe ages, something subtle continues to happen. It becomes more transparent. In its earliest epochs, neutral hydrogen-filled space, absorbing high-energy ultraviolet light. Over time, radiation from the first stars and galaxies reionized that hydrogen, making the universe clearer to energetic photons. As expansion proceeds and matter thins out, interactions become less frequent. Space grows ever more diffuse, ever more transparent. The cosmos is cooling, it is expanding, it is thinning. Light travels farther without obstruction. Gravity continues shaping structures, but on the largest scales, emptiness spreads. From the faint microwave glow surrounding you right now to the cold voids between galaxies, from silent stellar collapses to black holes merging in darkness, the universe reveals a profound truth. Not everything announces itself with brilliance. Some of the most powerful events are invisible. Some of the oldest light is nearly imperceptible. Some of the most dramatic transformations occur in silence. We exist inside a bubble carved by ancient explosions, surrounded by the whisper of the Big Bang, drifting through an expanding cosmos that is gradually becoming clearer and colder with time. And here's a small question to leave you thinking. What is the approximate temperature of the cosmic microwave background that fills the universe today? As we slowly come to the end of this journey, take a moment to think about how far we've traveled together tonight. We began in Chapter 1, at the very beginning of the story, exploring the earliest moments of the universe, when space, time, matter, and energy first emerged from the silence of the Big Bang. From there, Chapter 2 carried us into the birth of the first stars, the pioneers that lit up a once dark cosmos. In Chapter 3, we watched galaxies begin to gather and shape the large-scale structure of the universe, forming vast cosmic cities of stars connected by invisible threads of gravity. By Chapter 4, we drifted through nebulae where new stars and planetary systems quietly take shape, reminding us that creation in the universe never truly stops. The journey continued in Chapter 5, where we looked closer at the powerful forces that shape stars throughout their lifetimes, the balance between gravity pulling inward and nuclear fusion pushing outward. Then, in Chapter 6, we stepped into the dramatic endings of massive stars, witnessing the spectacular explosions that scatter the elements of life across space. Finally, in Chapter 7, we reflected on how those scattered elements eventually become part of planets, oceans, mountains, and even the atoms inside our own bodies. Each chapter revealed a different layer of the cosmic story, showing how everything in the universe is connected across immense stretches of time and space. If you enjoyed drifting through these early chapters of the cosmos, there is so much more waiting ahead. The universe is filled with mysteries still unfolding: black holes, distant exoplanets, strange cosmic phenomena, and stories written in the light of stars that have traveled billions of years to reach us. So if you'd like to continue exploring these quiet, fascinating journeys through space, consider subscribing to the channel and turning on notifications. That way, the next time we set out to explore another corner of the universe together, you'll be right there with us. And if this video helped you relax, learn something new, or simply feel a little more connected to the vast universe around you, take a moment to leave a like and share your thoughts in the comments. I'd love to know which chapter fascinated you the most: Chapter 1, Chapter 7, or somewhere in between. Your curiosity and support help keep these stories going. Until the next journey through the stars, take care, rest well, and remember, the same universe we explored tonight is not only above you in the night sky, it's also quietly alive within you.